The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, everyone. My name is Marwan Altai. I am a product manager working for SCIA in Belgium. Today I'm going to be with you to explain the content of the new solution, the fiber reinforced concrete in SCIA Engineer. Maybe before starting, I would like to check if the sound clear for you. Okay, so we can move on. Before going to the details of this presentation or this webinar, I would like to check few things. Be sure that the sound is okay. If not, then you can use the sound panel to adapt or to adjust the volume. During the webinar, in case that you have any question about the steel fiber concrete or even about the concrete design in general, you can use this opportunity. I am the responsible guy for the concrete design in SCIA Engineer, and I would like to get your question. I will do my best to answer all your questions during the webinar, but in case that the time will not be enough, then definitely I will come back to you with some answers. Of course, this webinar will be recorded. You can find the record on our website, www.scia.net. Also, you can find it in our YouTube channel. The content of this webinar, it will be regarding the new material, regarding the steel fiber concrete. I will explain to you how we built up this new library, how you can use it. Also, we will discuss today the calculation of the internal forces, what's the differences between using a steel fiber concrete and obtaining the internal forces for traditional concrete floor, for instance. Then we will talk about the capacity check, and the last part will be about the supported checks in SCIA Engineer regarding the solution for ULS, SLS, and the last part, it will be for the nonlinear calculation. Next point I would like to mention is about the steel fiber concrete. In fact, this project has been done based on a deep collaboration with Bekaert. And for those who they don't know Bekaert, in fact, a company who producing a steel wire, different types of steel wires, not necessarily be the steel fibers that we use in the concrete, but they are also producing several types of wires, like the wires that could be used with the tires, the wires could be used also with the book binders, etc. So they are, you can call them as a product leader in producing the steel wires. Today, for our topics, in fact, we will talk about three different types of fibers, which is used or which is produced by Bekaert. It's called the Dramex steel fiber. And today in our solution in SCIA Engineer version 18, you can use those three types of fibers in combination with a traditional reinforcement to reinforce your floor system. Maybe someone will ask what's the differences between the 3D, 4D, 5D, and why they are using this terminology. In fact, the name, it's linked to the form or to the shape of the fiber. This is basically how it is. The usage of those different types, you can use all of them, but finally it's somehow limited to the type of the structure. With some structure, you need to use 4D. With other structure, you need to use 5D. So I think you need to little bit understand the differences by reading some articles about that, or you can maybe contact Bekaert directly to understand which one is the best for your project. But from our side, as a software company, you can use all these types of fiber to calculate or to analyze your floor system. Now we can move on with the material itself, and there is something very important I would like to mention to you about the terminology that we use for the steel fiber as a material. As you can see, the name, it's a little bit longer than usual. If we compare that with the name for the traditional concrete, we use C30, 37, something like that. So with the normal concrete material, we use the class of the concrete as indication to the material itself. But with the steel fiber, it's a little bit tricky, and for that reason, we made the name a little bit longer to make it more easy for the user to understand. And I'm going to explain to you what's the meaning of all of that. The name will start with the C, something about the class of the concrete, the characteristic of the concrete, and then indication about the type of the fiber, 5D, 3D, or 4D, and then something which is the aspect ratio and the length of the steel fiber. So when you change something here, in fact, you are changing the material itself. Also, a letter to indicate the way how you are coating the steel fiber. And there are two options in SCIA Engineer, the bright and galvanized steel fiber. Then also the way how you are going to deliver the steel fiber to the mixture also will influence the material itself. And there are three options inside SCIA Engineer. And finally, some indication about the kilograms inside the mixture. So basically, this is the name that we use for the library. And when you generate something by your own, the name of the material will be adapted automatically. Next topic, the question could be how we obtained the residual strength of the concrete fiber concrete. In fact, if you read the German guideline, and maybe I missed to tell you that our calculation today for the steel fiber concrete, it's based on the German guideline. As you know, till now, there is no recommendation, there is no specification in the Eurocode about the steel fiber concrete. But you can find in each country there are several requirements or recommendations for that topic. But today we are using the German guideline as a code for the calculation and for the checks for the steel fiber concrete. And if you read the German guideline, they are explaining how you can obtain the residual strength, and they are saying minimum you need 6 tests to obtain that value. What we have in SCIA Engineer, we obtain the library based, as I mentioned, based on very good collaboration with Bekaert, and Bekaert made really huge tests to obtain that value. And this value, it's somehow influenced by the concrete class, the fiber type, and the fiber dosage. Not only that, also I would like to mention that in SCIA Engineer, there is some calculation happening in the background of the material. So when you change something, in fact, all the calculation of the final design value for the strength will be adapted automatically. But we start our background calculation based on precondition. We are assuming the value of this residual strength is equal to that value. Then this value will be multiplied by a factor from the German guideline to obtain the residual flexural strength. Then the next step, also this value, which is the last value from the previous stage, will be multiplied by a beta factor to obtain the basic value for the residual tensile strength. And the German guideline already explained to us how we can obtain the beta factor, which is something like that implemented in SCIA Engineer. Finally, in order to calculate the design value, the user would like to have a factor, which is the long-term factor, and also coefficient take into account the long-term effect. Those two factors can be modified from the properties of the national annex. Finally, if you look inside SCIA Engineer and open the library of the steel fiber concrete, you can see it as somehow divided to three parts, and this is what's important for us. The first part, which is the characteristic basic value, and then the residual tensile strength, and the final one, which is the design value of the residual tensile strength. Keep that in your mind. This is in fact what we use in SCIA Engineer inside the checks and inside the calculation of the dosage. So this is very important value, and I will explain a few things about those values later. Now, I'm going to show you that in SCIA Engineer directly, in order to not skip many things. First of all, I would like to ask you to not forget, when you would like to design a structure or to analyze a floor system containing steel fiber, please activate the concrete, traditional concrete as a material, as well as the steel fiber concrete. Maybe someone will ask me why I need to activate the traditional concrete as long as I'm just going to use the steel fiber concrete. In fact, we are using a big part of the formulas for the concrete design, from the Eurocode. Those formulas can be quite used also inside the steel fiber concrete. The part which is related to the checks itself, it's done by the German guideline. Other parts, we can take it already from what we implemented in the past regarding the concrete. That's why in order to activate the steel fiber concrete, always don't forget to activate the concrete as a material. This is the activation point of view. At the end of this webinar, I will explain to you the calculation, the nonlinear calculation, and now maybe just quickly to indicate that in order to do nonlinear calculation, of course, you need to activate the nonlinearity, and inside the nonlinearity, you will find 2D physical nonlinearity FRC, which is required to do nonlinear calculation for the fiber reinforced concrete. So those two items should be also activated in order to do nonlinear calculation. And now if we go to the library inside the concrete, you will find the fiber, and those are the three types of the fibers that we can use: 3D, 4D, 5D. As I explained to you here, you can find some parameters to change from the fiber itself. From the material, maybe someone can say this is complex situation. I need the library directly. Just from the project data, you can activate the material, and here you will find all the properties, which is I already explained to you. This is the first part, and this is the second part, and this is the designed value. Right? So this is the material itself. And finally, if you go to the concrete menu, you will find there is one sub-menu inside the concrete tree. It's called SFRC 2D member, and this containing the internal forces and the rest of the checks. I think this is clear to you, so I'm going to go back to my presentation. Next point I would like to explain is the internal forces, how we do the calculation of the internal forces. And the question could be, is there any differences if I will do the internal forces for a normal concrete floor compared with the fiber concrete floor? I'm going to explain that to you. Basically, SCIA do the internal forces calculation in the same way for traditional concrete and also for the steel fiber concrete. First of all, we calculate the elementary, how we call it, elementary internal forces, which is, as you are familiar with, mx, my, mxy, etc. Then in the next step, we calculate the principal forces, and we do the calculation in the center of the cross section and on the surfaces of the cross section on the top and bottom side. And finally, we calculate the design forces. And in the design forces, we use a Bowman, it's called the Bowman transformation method, where we transform the internal forces in the direction of the reinforcement. In fact, there are several advantages from using this method, and within this method we are also doing many things, like we take into account the effect of the torsion. We do some shifting to the bending moment to be compatible with the Eurocode, because there is one article in the Eurocode talking about shifting of bending moment. And also there is one advantage from using Bowman transformation method, which is not necessarily that you can use the reinforcement in 0-90 degree, how we used to do that. But now you can also change the direction of the reinforcement, for instance 45 degree, and then SCIA still able to calculate the internal forces and do the design or the check. Next part, I would like to compare the capacity of the traditional concrete section compared with the capacity of the steel fiber concrete. Today, keep in your mind, today in this webinar, always I will compare the steel fiber concrete with the traditional concrete, because I'm taking in my account that the majority of you very familiar with the concrete design, and it will be more sensible if I will compare it with something that I know. We know that the steel fiber concrete somehow a new tool today, not too many software offering a solution, and basically in Europe only SCIA offering that solution. So it could be that not all of you familiar with the way how you can design the steel fiber concrete, but if we will compare that with the traditional concrete, then the idea will be very clear. And now for the capacity. Probably you are familiar with this figure from the Eurocode. This figure explains to you how you can calculate the capacity of the cross-section and how you can make the equilibrium inside the cross-section. And as you can see from here, you have the tension part supported by the traditional reinforcement, and you have some compression in the concrete. Now the question, does that also will be similar in case of the steel fiber concrete? If we look inside this similar diagram, we will see almost we have the same element, we have the same forces, Fc, the forces in the concrete, and we have the forces here, Fs plus Fs minus, which is the forces coming from the traditional reinforcement. But there is one factor, which is the factor influenced by the exist of the steel fiber. So because of that, we are expecting now the new capacity of this new cross-section containing steel fiber could be bigger than the normal capacity of the traditional cross-section. So this is the first point. We should keep that in our mind. And also, if we will see this diagram, which is the Disatrous Strength diagram for the steel fiber concrete, somehow it's look like the diagram for the reinforced concrete, and this giving us the feeling that the steel fiber will behave just like traditional reinforcement inside the cross section based on that diagram. So we will see how much the steel fiber can participate in the capacity of the cross section, and if the steel fiber will participate in the capacity of the cross section, then it could mean I can reduce a little bit something from the traditional reinforcement inside the same cross section. At this point, in fact, take me to another subject, which is the calculation of the dosage and the calculation of the capacity itself. The way how we calculate the capacity inside SCIA Engineer, in fact, SCIA assuming that a same amount of kilograms of fibers exist inside each mesh. for instance, we start from the maximum amount of kilograms in each mesh, and then we obtain the unity check for the capacity. And if we see the unity check, it's far away from 1, then we make another iteration, we reduce the kilogram, and this kind of a process, it's done in SCIA Engineer to obtain the optimal value of the kilograms. So we do that in 2 directions. We do that for the top and for the bottom layer. So 4 times we calculate the capacity of the cross section to obtain the optimal amount of kilograms inside each mesh of your slab. And finally, when you go to the brief output, you will see the brief output represented by that. With it, you can see the internal forces, the resistance forces, etc. I think it's still maybe not clear to you what is the advantage and why should I use the steel fiber in combination or without even the traditional reinforcement. So I will try during this webinar to quickly explain the advantage of using the steel fiber, but definitely the time will not be enough to explain all of that. So I will focus on few critical points. Let me show you, for instance, this project. In this project, what I made, I have 2 examples. I have a slab supported directly on the soil. You can call it a mat foundation, something like that, containing a steel fiber. I use 30 kilograms per meter cube. I'm using 5D steel fiber and exactly the same floor system, but with the traditional concrete. I am a little bit curious. I would like to see what's the differences between them. As I indicated to you, if we are talking about the internal forces, let's check the internal forces for the traditional concrete. As you can see, from 0 to -10. If we go to the internal forces inside the floor system, which is containing fiber, also we're talking about the same internal forces. So this concludes what I already mentioned to you. The calculation of the internal forces will not be influenced by the fiber itself. So we're talking about the same floor system, in fact. Now, what I have in the tree, I have the internal forces, I have the dosage design. Inside the dosage design, you can select one floor, different, so the behavior of SCIA Engineer is exactly the same. Then you can select the load combination that you would like to use to obtain the optimal dosage amount. And I'm doing the calculation in node average in this case. If I will click refresh, then now what's happening? SCIA calculated the kilograms which is necessary to obtain the best unity check for the capacity. So as long as I'm limited between 20 to 34, then I'm expecting that the capacity of my floor system without any traditional reinforcement should be okay. Now, if I will go to the capacity using the same combination, everything should be the same. And if I would check the unity check, I will see it, everything is green. That means ED is less than MRD, something like that. Okay, I will go back to the capacity. There is something I would like to mention. In some cases, I would like to show you it like that. In some cases, you will get the result like that, blank. There is no result inside it. And this, in fact, it's an indication from SCIA Engineer to the user to tell the user that the required kilograms is more than 35 kilograms. What I did, in fact, I just removed the averaging of the peak. So we have huge citruses here, and that's why without the activation of the average strip, SCIA will calculate the fibers here, and the required fiber will be more than 35. So this is indication from SCIA Engineer to the user to tell him, be careful, your economy, the cost of your floor system will be too much. And that's why we are hiding a little bit the result. Let's go back to the original case where I don't have any issue and the maximum 34. I calculated the dosage and the dosage is shown like that. I can present the dosage inside the tables. I can send it to the engineering report. Now, the question, should I use 34 everywhere or should I divide it? This is something up to the designer to decide. Next, I will go to the capacity. I already did that. Inside the capacity values, you can see MRD, and you can find an RD. Now, the question, how can I know that because I decided to use the steel fiber here only without traditional reinforcement, I can save some reinforcement, traditional reinforcement from the same system? As I told you, we're talking about the same project. This one has no traditional reinforcement, just like this one, but even without steel fiber. And if I will go to the reinforcement design, inside the reinforcement design, you can find a value which is called required statically. Required statically, it means only the static reinforcement which is required to obtain the necessary resistance. So there is no detailing provision taken into account. And if I will calculate, you will see, this is shear. If I will calculate, you will see that SCIA required you to put some reinforcement inside your slab. This is the top reinforcement. If I will go to the bottom reinforcement, something like that. Okay, that's mean in order to obtain the necessary capacity for this cross section, I need to put the reinforcement, the traditional reinforcement, but this amount of reinforcement will not be required in case I can use the 34 grams of the steel fiber somewhere under the columns, and then the rest could be only 20 kilograms. I hope the idea is clear for you with this comparison, how you can obtain better resistance by using only the concrete with the steel fiber without using the traditional concrete. Let's go back to the presentation. And now I'm going to talk about a very interesting topic, which is the shear force check and punching design for any floor system containing a steel fiber. Again, I will do the comparison with the traditional concrete to make it more clear to you. Basically, as you are familiar with, in order to calculate the value of VRDC, we are using this formula. This is from the Eurocode. And then we also calculate, however, for the calculation of the VRDC, but with the steel fiber, the formula is a combination of two things, VRDC plus VRDCF. And this is the extra value could be added to the VRDC due to the participation of the steel fiber in the resistance against the shear. And this is the formula from the German guideline. And here they are explaining to us how we can calculate the value VRDCF. And finally, this is the explanation also about how we can calculate the shear stresses around the column at the first control parameter and at the face of the column, U0, U1, as you are familiar. So what I would like to say, in fact, the principle of doing the shear check or the punching design is exactly the same when you have a steel fiber concrete. Only we have to take into account the participation of the steel fiber in the formula. And the German guideline indicated like that. This is for the shear check and this is for the punching check. This is a quick comparison with the Eurocode regarding the design. What you can see now on the screen, I made two examples, two identical. The only difference, I have within this slab in fact supported by several columns, but inside this slab I use 30 kilograms of steel fiber, and in this slab I use nothing, just traditional reinforcement. Okay, and as you can see for the slab here on the left side, the internal columns will not require any punching shear reinforcement, while the traditional slab with the traditional reinforcement, I need to put extra reinforcement due to punching requirement somewhere here. And if we look to the differences in the values itself, we will see that if I will make it a little bit like that, if we will compare the VED, we are talking about the same VED, the bending moment. Just for your info, here we have the slab with the steel fiber, here the slab without the steel fiber. So we talking about two identical cases. The differences is only here, with and without. The effective depth of the slab is the same. The calculation of the critical parameter, it's the same. The only difference that we have it's here, the calculation of VRDC. And you can see when I'm using the steel fiber, the value of VFVRDC is higher than the value when I have a normal concrete. I will make that more clear for you by going back to this example. I'm going to do the shear checks now with the same combination, everything is the same, and I'm using the design. Keep in your mind something very interesting. With the calculation of the capacity, maybe I missed to say that, you can use several, or you can use different values for the kilograms. You can ask from the software to use the kilograms, which is defined already in the material at the beginning of your project, or you can use the designed value. It means that SCIA will calculate the necessary kilograms automatically and use that value to obtain the capacity, or you can decide the capacity by yourself based on the kilograms that you will input. So let's run it like that. I have 30, and of course I will get some problems here, because if you still remember, it was required 34 kilograms. So if I will make it 35, for instance, and run the check again, you will see the capacity check will be fine. This is something quick. I missed to explain that to you about the selection of the dosage. The same thing it will be with the shear, with the punching, with all these checks. I can play with the kilograms that we have. And now I'm going to do the capacity, not the capacity, the shear checks for this floor system. And I will compare the shear resistance of my floor system here with the traditional concrete. What I'm going to do, I'm going to go to the table result, and let's delete this result and generate them again. I'm interested in comparing this point here. As I remember, it was 73. So here in this item, in this point, I have this calculation. So I'm going to pick that, copy. I will put it somewhere here to compare the result. And then I will do the same things, but this time for the same point on my traditional concrete. So I will calculate it for that system. And here I will go to the shear reinforcement, and the point should be 360. Yes, 360, as you can see it. So we have exactly 2 points where we can compare the result. I will take also this result, and I will put it in the same place. So let's see what's the differences between them. What important to know is this value, in fact. If we see, this is in fact the value of VRDC coming from the system containing steel fiber. And this is the value VRDC coming from the system which is not containing steel fiber. As you can see, those two values, the value from the steel fiber, it's higher. And the question which could come to your mind, why 86 become 106? If we go back to the presentation itself, what the code said that for the calculation of the VRDC with steel fiber, the value of VRDC should be taken from the Eurocode. It's exactly the same. Then why I have a different value? Because this is the participation of the steel fiber, but I'm expecting to have exactly the same VRDC in both cases in my example. However, I don't have. There is something mentioned in the German guideline, and they are saying in case that you are going to use a system containing steel fiber without traditional reinforcement, then in that case you can use the full cross section. Normally when we do a design, we have reinforcement somewhere and we're talking about something, we call it effective depth. As long as in my system here there is no traditional reinforcement, then I can use the full height of the cross section. And now if I will do some quick hand calculation, I can see the 86, if I will have the 86 divided by 165, which is the D effective, multiply by 200, and then this should give me a value equal to 104, which is close to this one. I'm doing that quickly. So my point from this comparison, that not only the participation of the steel fiber will help you, but also in case that you decided to not put traditional reinforcement in your system, you can use the full height of your cross section, and this will give you a value higher than what in your VRDC. And then according to the German guideline, this value should be added to this value, but we should take into account there is a limit, and the limit, I think it's taking the maximum between them. And finally we obtain the value which is with F, and this value will be used for the unity check. If we go to the shear check again, and this is the value. So we have VED 379 and the value VRDC 106 and VRDC F 106, and finally we have the value VRDCF. The German guideline also in punching, they gave a limit that should not, let's show it here. Here, and this, the value of VRDC should be not more than 1.4 multiplied by VRDC. So if you if I use the calculator now, if I will multiply 106 by 1.4, somehow it should give me a value close to this value. Yes, it's 148. I think now the idea is clear how you can how the steel fiber participating in the resistance of the shear and also participating in the resistance of the punching. For the punching, this is the example that I made. We can see it quickly. We are already running late. Punching, I'm doing the punching now. Current, all. So now, as you can see, just for your information, the colors in SCIA Engineer indicating the case. So if it is a green color, it means there is no punching reinforcement. I will do the same for the traditional slab with the same things. All check. And the blue color to indicate that some shear reinforcement or punching reinforcement should be required here. I'm sorry, I need to move faster than what I'm doing now. Next checks I would like to mention, it's the cracks calculation. Again, the procedure of the cracks calculation is quite similar to the traditional concrete. We have two values. We calculate the cracking stress. We compare it with sorry, with the stresses inside the concrete, and we're using this diagram. So basically, the principle exactly the same: calculation of the stress per direction, calculation of a principal stress, then we calculate the angle, etc. So the principle is exactly the same, but I still want to see the differences between the traditional concrete and the steel fiber concrete. And here in the Eurocode, if you would like to design a structure and take into account the calculation of the cracks, then the Eurocode indicating 7.8, 7.9, 7.10, I think also, and 7.11. This is the way how we calculate the cracks in the Eurocode. So the crack size is the value of obtained from the multiplication of the spacing between the cracks multiplied by this strain. Now the question is that also will be valid for the steel fiber concrete. In fact, yes and no. It's almost the same formula, but we should take into account the participation of the steel fiber in that formula. As you can see, it's exactly the same, only this is the difference. And here the German guideline explains to us how we can calculate the differences in the strain. And this value, in fact, it's exactly the value like here, but it's multiplied by 1 minus alpha. And alpha, according to the German guideline, it's something less than 1. So in fact, the value when we are using the steel fiber concrete of the strain is less than the value in the traditional concrete. The same story for the SR max, almost the same formula multiplied by this factor. Let's see what does that mean in SCIA Engineer. For that reason, I prepared the three models. The first model is a beam, but I gave it a dimension of slab to simulate the behavior of a slab, but on 1D member. So it's a beam 1 meter width, and the thickness is 200 millimeter, has only traditional reinforcement. The second one, I have a slab with the same amount of reinforcement, everything identical, but it's a slab. And the third example, it's the same slab, but this time I combine the traditional reinforcement with SFRC, with a steel fiber. And I calculated the cracks. In a case, in the beam case, I see the cracks appear, but the unity check is not okay. And if I will go to the second case, again, the cracks appear, but the unity check is not okay. And now if we go to the steel fiber, we will see that the cracks appear, but the unity check is okay. So the steel fiber made some magic inside the system that I have, and I would like to understand why, as long as we're talking about exactly the same, why or how the steel fiber participated on that. So if we look inside the result itself, you see the result for beam RC without steel fiber, and this is the result of the steel fiber. What we need to look, let's check first if we're talking about the same internal forces. Almost it's the same internal forces, so 78, 78. If we go to the stresses in the steel, 524, 524. If we're talking about the tension in the concrete, 11, 11, 11. So we're talking about almost the same thing. Then still the question, why I have unity check in the steel fiber better? For that reason, if you would like to read a little bit inside the German guideline, then you will find this statement, which is a nice statement. They are explaining the behavior of the steel fiber inside the material itself. And they are saying the effect of the fibers leads to reduction in the forces that the reinforcement steel has to resist. What's the meaning of that? In fact, the meaning of that, we will obtain a strain less than compared with the traditional concrete, and also we will obtain SR max less than compared with traditional concrete. Let's check those two results if that's correct. If we look to the traditional concrete, we have a value of 210 for the SR max, while here we have 132, correct? And then the second value, it's 2.22 divided by 1,000, and here we have 12.9 divided by 10,000. So again, this is less than. And now if I will do some hand calculation, I would say 12.9 divided by 10,000 multiplied by 132.9, and this gives me a crack width equal to 2.7.1, and this is the value. And now if you multiply 210 by this value, you will obtain a value of the cracks equal to 0.4, and 0.4 it's bigger than 0.3. That's why the unity check is not okay, but the unity check for the steel fiber concrete okay. Now still something in my mind. I don't know if you noticed that or not. Here when we're talking about the unity check, we will see a smooth curvature for the traditional concrete, the same thing for the beam. Why the curve of the unity check weird little bit, look like Batman head, I don't know, but it's a little bit weird. In order to explain that to you, I'm going to the model for that part. The three cases that I made, and concrete, crack. So I'm doing the cracks for SLS, as you can see. Now, so as you can see, the unity check, it's somehow variable. Definitely it will be variable for one reason, because we ask from SCIA to calculate the crack width based on the designed dosage. So the dosage here not necessarily be the same dosage here. But now if I will change the dosage to let's say 35 and do the calculation, now we can see the same behavior or the same curve, because the value of the kilograms is exactly the same everywhere. So I hope this idea is clear to you. And now this is the value for the unity check. If I will compare it with 2D, the same combination, everything should be the same. I have the value, not okay, and I can do also the cracks for 1D design, same load combination, and here it's crack, unity check, it's 2 point something. So I think this is clear now. We can move on with the presentation. I will little bit review the advantage. We said for the capacity we can use the full height of the cross section in case that we don't use the traditional reinforcement, and this has some influence on the capacity and on the shear capacity. We said also the steel fiber will participate in the resistance of the shear. We saw that, and now we are talking about the cracks calculation, and we have seen how the steel fiber will influence the calculation of the cracks. Next topic is the Disatrous limitation. Basically, there is no differences between the traditional concrete and the steel fiber concrete, but be careful. The differences will be there in case you will do nonlinear calculation. But with the linear calculation, in fact, there is no difference. The result very identical. So this is the result from the traditional concrete, and this is the result from the steel fiber concrete. As you can see, is copy paste. There is no difference. But if I will do nonlinear calculation, then the story will be different. Next topic is the nonlinear calculation. In nonlinear calculation, again, don't forget to activate the nonlinearity and activate the physical nonlinearity for FRC. Keep in your mind also, we developed those two things in version 18. So you can do nonlinear, physical nonlinearity for traditional concrete, then you need to activate this box. And if you have steel fiber, then you need to activate that box. For nonlinear calculation, the user can find several or two different types of stress-strain diagram. This diagram with a peak value in the tension side, and in some cases it could be that you would like to speed up the calculation, then you can pick the value like that without any peak. For the reinforcement, as usual, we use those two diagrams for the reinforcement, with stiffening and without. Before I forget to mention that in SCIA Engineer we use the material damage model, which is called MAZARS. You can find on our online help some explanation about this method, and you can find the reference of that to understand what I mean by that. Also, we're using a Newton-Raphson method as a method for the calculation for nonlinearity. The user can increase or he can change number of increments which should be applied on the load, and the user also can increase or decrease the number of iteration should be combined with the nonlinear calculation. In SCIA Engineer, we made a lot of tests to be sure that the method that we use in the physical nonlinearity is correct, and it's give a result close to the reality. Also, we studied the influence of changing the mesh size on the result. As you can see from this diagram, this is the load deflection diagram, and this result from example from the reality, and this is from SCIA Engineer, and you see some influence from the mesh size. Also, we studied the cases if you pick with peak value and without peak value, and you can see the result from with peak. It will give a result close somehow to the reality. Next benchmark I would like to explain is from this model. It's a slab containing steel fiber, and it's fixed support. We did the calculation in SCIA Engineer, and we did the calculation by hand. And based on those formula, we calculated all the forces which will lead to obtain the cracks moment and the cracks forces, and the result was quite nice. As you can see from the diagram, this is the diagram between the load and the stresses. The behavior of the material, very clear, it's a linear from load up to 15 until we reach a 15. This will give us a stress equal to 2.85, something like that approximately. And if we will compare this value with the diagram from SCIA Engineer about the stress strain diagram, then we are talking about, in fact, this point. And this point, we have a value of strain equal to 1 and value of stress equal to 3. So 2.85, I think it's quite okay. So we are here, and then if we move in the load, here it's already mentioned that the 15 giving us the cracking moment. After 15, then the cracks will start appear. Then in fact we will go down like that, which is the representation of that part, and then we will reach a value of 1.22 stress, which is somehow close to 1.29. And then some stiffening will happen in the stress like that. So this is increasing until the failure. So I think the behavior of the material quite nice based on the calculation of SCIA Engineer. Also, if we compare the strain diagram, you will see also the material up to 15 behave in a linear way. Then after 15, we will start that the strain start increasing. So after 15, in 15 we are here, it should give us 1.0, and in our case 0.8, and then after 15 we will go to this point where it should be close to 3, so it's somewhere here, and then finally up to failure, which is 35, it will go somewhere here. So in my point of view, the simulation of the material, the physical nonlinearity, quite nice in SCIA Engineer. I'm going to show you that example. So this is the result. I already did the calculation, the nonlinear calculation. It takes some time to obtain accurate result. So I already did that. What I'm going to show you is the result. So this is the basic stress. As you can see, it's 0.89. I will increase the load. The stress will increase. Then until 15, we will reach somehow the maximum that we can obtain. And then after 15, we should get some drops in the stresses. And then if we reach to 35, we get the failure here. So there is no stresses. If we will do the same basic strain, then it also somehow close to reality. So the failure should be somewhere in 300. So this is 258. I think that's okay. Not only the benchmarks that we did it by ourselves, but also there is something I would like to mention. It was made in China, and from this university. I don't know how to pronounce the real name, but let's say Tongyi University. A team of researchers from that university worked with a team of researchers from Bekaert company. They somehow studied a pile cap slab supported by those piles, and in fact they made two models, and the idea was to compare the models with the analysis from Bekaert. So the first model, it's a part of the slab containing one pile and supported by 4 hydraulic jack, and the second one containing 4 piles with 1 hydraulic jack. The result was they made it like that. This is the result for the real system from the reality, and this is the result from model 1, where you have 1 point in the center and point in the corner. And this is in fact, this one, it's just something like that. I mean, if I would like to take this one, in fact they are reading the result somehow like this. Yes, somewhere like that. Okay. And then this is some image about the way how they made the test. This is the hydraulic jack, and they made several cases with using 30 kilograms of the fiber. The idea is to obtain this diagram, the load deflection diagram. What we did in collaboration with Bekaert, we made the same model, but we pick a quarter of it. So this is the quarter of the model, and this is the location where the hydraulic jack should participate. And we made that model, and we calculated the result. The conclusion of that kind of benchmarking is this is the result from SCIA Engineer, and as you can see, it's quite close to the calculation which was made by the researcher in the university. And the conclusion of that benchmark, which was written by them, they are saying SCIA Engineer gives a very accurate prediction of the structural behavior, the collapse load and the first crack load. Also, they are saying giving a similar design result if you are using a yield line theory. So if you would like to do that by yourself and compare, the results should be quite close. And then give a possibility to design a complex structure. And also they are saying SCIA Engineer can design a fiber only or fiber plus steel fibers in combination. So almost I'm done. This is the conclusion of this webinar. I explained to you the content of the material. You can easily pick the necessary material. You don't need to define anything from your side. All the material already defined in SCIA Engineer. Just activate the concrete and the fiber concrete as a material. I explained to you how you do the design of the kilograms, how you can do the calculation of the capacity, what the differences between the capacity between the fiber system and non-fiber system, and then quickly I explained to you the ULS and SLS checks. And the last few minutes, it was about the nonlinear calculation. I'm sorry because I couldn't spend more than this on the nonlinear calculation. It's already done the hour that we have it. Now I'm going to read your question, and I will try to answer as I can. Please feel free to type your question now. Not only about the steel fiber concrete, but even if you have something about the concrete design in SCIA Engineer, it's still my responsibility. I would like to see how you think about the solution. If you think that you have some ideas to improve our solution in SCIA Engineer regarding the concrete design or regarding the steel fiber concrete, just please feel free to send me your email address, or just tell me. We can have a meeting online and we can discuss that together. So let's see what we have from the question now. Well, the first question is about someone asking if the design of the steel fiber reinforced concrete covered by the Eurocode. Based on my knowledge, there is nothing mentioned about in the Eurocode at this moment. We are expecting the new version of the Eurocode, and we hope it will contain some information about the steel fiber concrete. However, you will find in each country different or some specification or requirement, or you can call it recommendation about the steel fiber concrete. For instance, for the Eurocode, there is a model code where you can find a lot about the steel fiber concrete. We made our calculation based on the German guideline at this moment, and we will see how it will be in the Eurocode in the new version. I don't know if it is 2020 or 21. We don't know. The next question is someone asking about is in SCIA the input of the kilograms of the steel fiber will be inputted by SCIA or by the user. I think this is what I understand from your question. Definitely inside the material library there is amount of fiber. Maybe I can show you that again in SCIA Engineer. If we go back to the material, as you can see, this is the material. Here you can see, what is it? Here you can see the kilograms. So the material, inside the material, you already can see the kilograms inside it. This amount will be optimized automatically by the software, or you can decide it by yourself. I hope I answered your question. Can you send the presentation? Of course, I will do that. Do you have a radial reinforcement solution for the circular slab? I'm not sure if I understand the question, but yes, based on what I understand, I think you are saying if we can input the reinforcement in a radial way, does that take into account? Yes, if you can do it, if you can model it in SCIA Engineer, then these kind of practical reinforcement will be taken into account in combination with the steel fiber. Is there any factor that is there any safety factor which account for the fact that the fiber may not be 100% uniform? Yes, there is a factor. You can read our online help to find out what's the meaning or how is the behavior of that factor. Is there a minimum amount of fiber required? Yes, the minimum amount is 20 kilograms in SCIA Engineer. In reality, I'm not sure how much in life, the designer doing that. But in SCIA Engineer, we have a limit of the steel fiber between 20 and 40. For the capacity check, it will be linked to, fixed to 35. What about the concrete cover for the concrete fiber? The traditional method is still be valid for it, yes, but keep in your mind, if you don't have if you don't have traditional reinforcement in your cross section, then we will take the full cross section as effective depth. This is really a good question. Why there is some differences between the beam and the slab? I think you are talking about the cracks calculation. In fact, I didn't check that, but it could be that due to the 2D behavior. I'm going to check that and see. I have your email. I'm going to contact you to see if you find that as something weird. But I don't think the differences was quite different, because I still remember the calculation of the crack moment. It was exactly the same. It was only the unit check different, but I'm going to check that later. Are the ULS checks also coming from nonlinear calculation? It's in fact in SCIA Engineer, the behavior, it's like that. Cancel. If we go to the checks, then it's up to you to select nonlinear combination or linear combination. So there is no link between them. So it's up to you to decide if you would like to use nonlinear or linear. Some other question is about concrete. I'm going to answer this question later. If we use only fiber reinforced concrete without ordinary steel rebars, yes, but I don't know the rest of the question. Yeah, this is very nice remark from someone who's saying we don't need to apply a minimum quantity of traditional reinforcement in case we have a steel fiber concrete. That's fully correct. In case that you will put the steel fiber with a mixture, then you don't need to put AS minimum inside your cross section. Is there a software demo for student? For student, you can ask for free license if you would like, and you will get that as a part of your license. Someone asking me, can we use a different type of steel fiber? Now we're talking about Dramix fiber, which is produced by Bekaert. Can we use a different type of steel fiber? Basically, yes, you can use different type of steel fiber. I'm going to go back to the library itself, but it needs some preparation from your side, because as I indicate to you that the material properties, it's calculated automatically. As you can see, you cannot change it. But if you deactivate this tick box, then you are able to define your design residual strength by yourself. So if you have a different steel fiber, but you know the residual tensile strength, then you can input those values, and then you can use those values in the check itself, because the German guideline did not mention if we are using this specific type of steel fiber from this producer or from that producer. The formulas of the check valid always for any type of steel fiber. The only difference here is the properties, and the properties it can be modified by yourself. Can we combine fiber with the classical reinforcement? Yes, you can combine. Okay, I think the rest of the question, it's somehow kind of question about the concrete design in general. I don't want to take your time. I'm so happy, I'm so glad that you joined me in this webinar. To repeat that, please, you can rewatch, you can check it later. From tomorrow, we will publish it in our website and our YouTube channel. Last thing I would like to indicate is please take this my email address. Anyone who would like to participate in making SCIA Engineer really better, then please contact me and send me your email address. I will be glad to communicate with you. So thank you very much and have a very nice rest of the day. Bye-bye.